So the lecture for today that I'm giving is on the measurement problem in quantum cosmology. At least that's what I originally planned, but since you had a workshop that thoroughly covered this topic last year, I decided to emphasize a few other things that I've done in my research. So this lecture is a lot more based on published research that I've done, unlike the last lecture, which I think was more just a general overview and not very much based on my own research. So I thought I would highlight kind of three things that are in some ways connected to this general topic. So the first is about the measurement problem. The work I've done related to that focuses more on how we can think about the measurement problem arising in classical statistical mechanics. So I want to make an analogy between a possible kind of interpretational problem that you can raise in classical statistical mechanics that has some similar features to the quantum measurement problem. So that's the first part of the lecture. Then I switch more to talking about the measurement problem as it arises in quantum cosmology in the broader sense as I was talking about yesterday. So this has to do with inflationary cosmology in particular, and how inflation is seen as a kind of a mechanism for generating the inhomogeneities that give rise to eventually structure formation in the universe. Okay, so I'll talk though first about inflation a little bit, what it is, and the fine-tuning problems that originally motivated it. So that's something I've written a few papers on. And then the last part of the lecture will really be properly on the measurement problem in quantum cosmology. Okay, so the quantum measurement problem, I think, is like most scientific problems, not some single problem. It can be understood to problematize quantum mechanics in a variety of ways. Some of them maybe have a more scientific role. Some of them we might think of as just more merely philosophical or interpretational. And the reason that there can be many quantum measurement problems is because scientific problems in general depend on how we interpret them. And this is something I'm taking especially from the work of Nichols, which I used a lot actually in my dissertation. And one interesting thing that Nichols and others have noted is that a lot of things that we think of as scientific problems are only recognized as a scientific problem after the fact. And this is true of some of the problems in inflation. I mean, after a compelling solution has been provided, so because Guth saw inflation as a solution to various problems, suddenly those problems became like real problems for cosmology, whereas in the past they weren't considered problems at all. So it's really the solutions that often are the main motivation for thinking of something as a problem. So of course, as we all know, whether we regard the quantum measurement problem as a genuine scientific problem or a philosophical problem or merely a pseudo problem, it's been the centerpiece of philosophical discussions in quantum foundations for decades now. So I'm sure you're all very familiar with it. I think nowadays a lot of people like to cite this paper of Maudlin's, this three-measurement problem paper, because it gives a nice sort of easy, clear formulation of the measurement problem as a kind of trilemma. So I'm going to present that first, because in my paper on statistical mechanics, in my papers, I make use of this as well, like a lot of people. So Maudlin sets up the measurement problem as a trilemma based on the inconsistency of the following three plausible statements. So the first one is that the wave function of a system is complete, or in other words, the wave function specifies all of the physical properties of a system. The second is the wave function always evolves in accord with a linear dynamical equation. In most cases, that's the Schrödinger equation. And then finally, measurements of some observable or property or whatever, measurements of, for example, as he puts it, the spin of an electron always, or at least usually, have determinate outcomes. That's the key phrase there, determinate outcomes. So that is, at the end of the measuring device is either in a state which indicates spin up for a spin measurement and not down, or spin down and not up. Okay? So these three, so Maudlin in the paper argues how these three are inconsistent. I'll skip that. Just to and conclude that denying one of these statements resolves this inconsistency, and at the same time we can think of it as suggesting a possible interpretation that solves the quantum measurement problem in this guise. So if we reject the first statement on the trilemma, then we maintain instead that the wave function in the system is incomplete. It needs to be supplemented in some way. For example, the Bohmian mechanics version of quantum mechanics can be seen as solving the measurement problem by denying that first statement, by adding some hidden variables or whatever. Okay, if we deny the second statement, then we suppose that the wave function does not always evolve in accord with the linear dynamical equation. That is, the wave function may undergo some kind of stochastic evolution, always stochastic, sometimes stochastic, something along those lines. And so various dynamical collapse theories like GRW or CSL fall into that category as interpretations that try to solve the measurement problem in this way. And then finally, we can deny the third one and maintain that measurements do not always have determinate outcomes. So we maintain that the wave function does not collapse in a way that universally determines an outcome, and the many-worlds interpretation is seen as solving the measurement problem this way. So this is, and since these are sort of the three popular interpretations that philosophers mostly discuss, the Maudlin formulation sort of fits nicely with how people want to think about the measurement problem. Okay, so much I think you probably already know. So in a couple of my papers, I kind of wanted to think about the novelty of quantum mechanics in light of the measurement problem by comparing quantum mechanics not to classical mechanics, but classical statistical mechanics, because classical statistical mechanics is a lot more similar to quantum mechanics than classical mechanics is, classical particle mechanics. Right. Yeah?
Can we just go back to the Maudlin trilemma?
This one.
So if we have epistemic interpretations of quantum mechanics, then I guess we still need some, would we just deny one then still, or we're still to set up already a bit of on-tick projects?
Yeah, I'm not sure. I guess it looks like we're denying 3, but I'm not sure. I'd have to think about it for a minute.
Because I guess.
I mean, it could also be 1. Maybe the analogy with statistical mechanics will bring that out, because most people have an epistemic interpretation of classical statistical mechanics. In that case, it's 1 that gets denied. Yeah. But maybe you could deny other ones. I don't know.
One is about the nature of the wave function, right? Maybe.
Yeah, exactly. Yeah, so if you sort of deny the reality of the wave function, then you suppose that the wave function is merely epistemic. So yeah, I think probably actually you're right, 1 is. But maybe I think you could also possibly deny 3 and have an epistemic interpretation. And maybe 2 as well. Maybe all of them are possible. Yeah, so I mean, one thing that people are interested in, I mean, when they think of quantum mechanics, we think of it as a revolutionary theory, and maybe it's less common today, but people often try to sort of identify what's conceptually novel about quantum mechanics. And I think a lot of people tend to think that the measurement problem is one of these facets, but I wanted to push back a little bit against the novelty of quantum mechanics being connected to the measurement problem. I want to say, yes, it is to some extent, but not as much as one might naturally think. That's because you can raise a parallel problem in classical statistical mechanics as well. And I doubt I'm original in thinking of this, but I don't know actually the history of proposals along this line. So, like I said before, classical statistical mechanics, in a lot of respects, is very similar to quantum mechanics. It's a statistical theory, just like quantum mechanics, and it has a very similar mathematical structure, actually, which can be brought out in different mathematical formulations. So, if we borrow Maudlin's trilemma for for quantum mechanics, I argue that you can present a classical measurement problem that's a trilemma based on the inconsistency of 3 plausible statements about classical statistical mechanics. So these are very similar to what I showed earlier, with some very small modifications. So instead of the wave function in classical statistical mechanics, we can talk about the statistical state of a system. The statistical state is a probability measure in classical statistical mechanics. So we can maintain that the statistical state of a system is complete. That is, it specifies directly or indirectly all the physical properties of a system by giving probability measures over all the observables, basically, indirectly or directly. Second statement, the statistical state always evolves in accord with a deterministic dynamical equation. Okay. In this case, it would be the Liouville equation. And third, measurements of observable outcomes always, or at least usually, have determinate outcomes. Okay, so you could argue, similar to Maudlin does, with small changes, that these three systems are inconsistent. Why? Because it's a statistical theory, basically. Yeah. And following up, you can do a similar thing and point out that we can resolve the inconsistency by denying one of those statements. Denying one of those statements also suggests a possible interpretation that solves this classical measurement problem. Yeah.
Can you say a little bit more about why we should think of them as inconsistent in the classical context?
Well, it's similar to the quantum case, actually. So if the statistical system is complete and it always evolves with a deterministic dynamical equation, then how do we get any definite outcome? We just have a statistical state. That's a probability measure that's evolving in accord with a dynamical equation. So it's like a superposition of different observable outcomes. So it doesn't have to, and so on. And you can go through it exactly parallel way. Yeah. So naturally, we learn statistical mechanics by thinking of particle states, but I've said nothing about particle states in presenting the problem in this way. But that's one of the solutions. We can say that the statistical state of a system is incomplete. We need some hidden variables. So if we supplement these by an interpretation in terms of particles, this is essentially what the Boltzmannian interpretation of statistical mechanics is like. Okay? And this is almost universally the kind of interpretation people give of classical statistical mechanics. Yeah, not universally, but pretty close. Of course, we could also deny the second statement and suppose that the statistical state doesn't always evolve in accord with the Liouville equation, a deterministic dynamical equation. It may undergo stochastic evolution. You can come up with a stochastic mechanics like this too, just like you can in quantum mechanics. And finally, you could deny the third statement. Measurements do not always have a determinate outcome. So that in this case, the statistical state doesn't collapse in a way that universally determines an outcome. And so we can contrive an interpretation that's in some ways maybe similar to a many-worlds one. Maybe you don't have to make the sort of many-worlds assumption per se. There's some room for interpretation in this third category. But in any case, Gibbsian, like modern kind of Gibbsian interpretations of statistical mechanics fall into this third category. And all these three are possible interpretations we can give classical statistical mechanics. Okay, maybe, the inventors of classical statistical mechanics never considered these other possibilities. These possibilities only really become live possibilities once we start thinking about quantum mechanics and the challenges it presents. But thinking backwards, they could have thought this way. Okay, just the fact that everyone pretty much interprets classical statistical mechanics as in an epistemic way, essentially, like the probabilities thereof, that doesn't erase the problem. Historically, there was never an opportunity for a choice among the alternatives for the reason I just said, that I think these various interpretations, alternative interpretations, only come around when we start trying to interpret quantum mechanics, which is more complicated in important ways than classical statistical mechanics.
Sorry, this first bullet point, you mean is about statistical mechanics? Or
Yeah, this is about statistical mechanics. Yeah, of course not in quantum mechanics. That's the minority view in quantum mechanics, maybe ironically in a way, right? Yeah. And my, put it up here, but it's an interesting fact then, like if it's possible to interpret classical statistical mechanics in these different ways, you notice that people prefer different interpretations across classical statistical mechanics and quantum mechanics. And you might think, why aren't your interpretive choices consistent? Yeah, maybe they should be, but maybe they shouldn't. It's a debate that one could have in philosophy of physics about this. Okay, but I don't think this, I think this really is an interpretational problem. I don't think any empirical evidence can decide between these cases. Yeah, why? Because, like, well, we don't see particles exactly. Yeah. So. Yeah, so I would argue that the alternatives I presented on the last slide are really just different representation of the same physics. So Frigg and Verndl have written many papers about Boltzmannian statistical mechanics, and more recently have compared Gibbsian interpretations of statistical mechanics with the Boltzmannian one, and they argue that there are differences, empirical differences. But I'm inclined to disagree with them about that because they make some interpretive choices that they don't need to make when it comes to Gibbsian mechanics. You could make choices of probability measures that reproduce exactly the same thing as Boltzmannian statistical mechanics. Okay, but I'm not going to argue that here. That's just a claim I'm leaving out there. In fact, I mean, these things, these different interpretations are just different ways of describing the same physics. Okay, so one thing I don't want to argue here is that there's no such thing as a quantum measurement problem, but I don't think that the quantum measurement problem that a lot of people have in mind is any different than a problem you could have in classical statistical mechanics. It's just a merely philosophical or interpretive problem. It doesn't have any real physical significance. But there are aspects of the quantum measurement problem that do have real scientific significance, I think. Now, I give a couple examples here. I don't know, which ones I would insist on or so, but I mean, the basic thing that distinguishes quantum mechanics, I mean, there's two things I would emphasize, I guess. Two things that distinguish quantum mechanics from classical mechanics. Maybe everyone believes this, but I'll just say it for the sake of saying it. One is entanglement. Okay, so we don't get entanglement in classical systems. And the second is non-commuting observables or operators. You don't have that in classical statistical mechanics. So that leads to quite significant differences. And this can be captured, for example, in a more mathematical form, like Miklos-Rede talks about this. So when we think of quantum mechanics being represented by von Neumann algebras, this leads to thinking, I mean, we can think of von Neumann algebras as a kind of like non-commutative probability theory. So in classical statistical mechanics, we just think of that in the context of probability theory. We can't do that with quantum mechanics because of the non-commutative operators. So we can develop a mathematical formulation that tries to capture this. But since we still give a probabilistic semantics to the observable outcomes of quantum mechanics, we need to devise some coherent probabilistic semantics to a non-commutative probability theory in order to understand the theory. Can we give an interpretation in terms of some kind of process randomness? It needs to be contextual in some way, and there's a lot of difficulties in understanding how you can coherently conceive this. That's one way maybe of putting the problem. David Wallace puts it in a slightly different way that I still think captures something about the significance of the problem, and it's related to the first one as well. But he says, on pain of failure to account for interference, we cannot, it seems, consistently treat the state as probabilistic, as a probability measure. On pain of failure to account for the probability rule, and more generally failing to make contact with observation, we cannot, it seems, consistently treat the state as representational. That's a slightly different way of putting it, but it's related to the first point as well. Yeah, and these kind of problems don't arise in classical statistical mechanics. Okay, I think that's the first part of the talk. I could pause here if anyone has any questions.
Can we go back to the previous slide just for a moment? It's not a question, I just want to see.
This one?
No, just the very, just that, sorry, just for a moment, I just want to read it to you.
Okay. Yeah. Well, but we're giving it and trying to give an interpretation that connects up to. I mean, we could just imagine a quantum system as it's just, you know, a vector in Hilbert space, you know, rotating around, but there's no physical interpretation of that. So we do need to connect it somehow to, yeah, the empirical observations, and we do that by using, yeah, I mean, as Wallace would put it, I guess, introducing the probability rule, the Born rule, and extracting, you know, like expectation values and things like that. So we have to move sometimes to treating the state as probabilistic, even though we can't when we want to account for interference. Yeah, so.
So yeah, it means the probabilistic semantics in the first.
Yeah,
that's okay, fair enough.
So yeah, I think Plus Lonesman also tries to solve the problem more in this way, but no.
Oh, yeah.
What's the difference between a scientific and a philosophical problem?
Yeah.
Is a scientific problem a problem which somehow must be resolved in a mandatory way in order to sort of account for observable things? Whereas a philosophical one is if it's just a matter of taste or basic principles. Or
maybe taste is a little too weak, but yeah, sure. I mean, maybe, you know, conceptual understanding is something we want to achieve. Whereas you may not really need that for the purposes of physics, or if we want to make scientific progress, improve the theory or something. Yeah, sort of like we were talking about yesterday, I think. There's some kind of success criteria for, say, quantum gravity that, you know, scientists may be happy with and think, yes, we succeeded here, whereas philosophers might say, well, we don't quite understand the theory fully yet. Yeah, so that's the kind of very vague, rough difference I'm appealing to here. And I think, you know, the classical measurement problem I've introduced here for classical statistical mechanics, it's philosophical in that sense. There's different ways we can understand the theory, and maybe in this case there's no reason to prefer one or the other. Maybe there is, I don't know. I haven't really had much debate about this with anyone, but yeah. I mean, like in my paper, I kind of try to advocate the third as a possibility, and the reason I advocate the third in the paper is because I think, I think because it's sort of underexplored, and I think it's interesting to consider the other possibilities. But, you know, if you're, so let me put it this way. If we think about, you know, how we tend to think about quantum mechanics, we usually, like I said earlier, tend to want to compare it to classical particle mechanics. That's very often like you know, when we think about a quantum to classical limit that we take, we're looking at that limit to see what happens in classical particle mechanics. But like I say here, you know, classical statistical mechanics is much closer to quantum mechanics than classical particle mechanics, and it makes sense to compare those. And if we're interested in an interpretational problem like the quantum measurement problem as presented here, it makes sense to think about the relation of those two theories that are quite close together, and to think of, you know, a kind of classical limit that relates those two things together because they're so close. And so then I think, well, if you're inclined to a kind of many worlds-like interpretation, you might be inclined to something similar in this case too. And similarly, like if you're inclined towards a stochastic quantum theory, then you might also be inclined towards a stochastic classical statistical mechanical theory too, and then you might be interested in looking at limits between those two, rather than going all the way to classical particle mechanics. I don't know, did that answer your question? But that's yeah.
So that last part that you said, so you think there are reasons to opt for the corresponding interpretations in both cases, or are you leaving that open?
Yeah, I leave that open. I would be interested in hearing people's reasons for against. I mean, I talked to Brian Roberts about this. He was kind of keen on the idea at the time when I presented this at the LSE quite a few years ago. And he said, oh yeah, he thought it was mandatory actually to have alignment between the interpretations. Yeah, I'm not so sure. There might be different considerations on either side that lead you one way or another. But yeah, he thought he could write a paper up that criticized Everett interpretations for not having the right alignment here. Although I think David Wallace's view about classical statistical mechanics, as far as I understand it, it fits more or less into this third category too. And he is very interested in the relation between the two theories. Yeah.
Yeah, and just I was wondering, isn't Wallace, for instance, connecting, isn't Wallace close committing to many worlds and Gibson rotation, and then on the other hand, this kind of classic formats, they are always committed to
That's right.
Boltzmann.
That's quite, yeah, that's yeah, that's where I kind of started in the paper, is noting that there's this very common link between 1 and 1 on the two sides, yeah, but less so down in the other ones.
I fail to see what's incoherent about Boltzmannian and Everettian. Why?
What's incoherent about Boltzmannian yeah, there's nothing incoherent about it.
I mean, if you're committed to an Everettian interpretation in quantum physics, I don't think that implies that you have to be a Gibbsian rather than...
Yeah, I don't know what argument Brian had in mind.
I don't think it's as mandatory as Brian thinks. I don't see the argument there really.
Yeah, well, I don't know his argument, so I think it was just his immediate reaction. He had some ideas, but I don't know what they are. So maybe he never wrote a paper about this. I mean, we talked about a little bit about writing something together, but yeah, I didn't materialize. But I mean, it's one possibility, though. You can imagine someone making some kind of argument that insists on commonality in interpretation, but I don't think it would be a particularly strong argument. But I think one thing I hope with my paper here is to convince people that they should maybe rethink their commitment to an interpretation if they haven't really, thought through why they're committed to that interpretation. So if you're committed to Everettian quantum mechanics with Boltzmannian statistical mechanics, you might want to pause a little bit and think, why am I committed to these two this way? I mean, maybe I should actually move to option 3. There might be reasons to, but maybe not. Maybe you find actually stronger reasons to hold the position than you did before. Oh yeah.
And do you think that this choice about whether to opt for alignment or not, are those going to be more conceptual philosophical considerations, or are they going to be, let's say, mathematical, about the kind of mathematical parallelism, or a little bit of both?
Well, yeah, I mean, I don't think the mathematics matters so much. So it would have to be some, I think, philosophical considerations.
So it forces people to rethink philosophically why they are committed to this interpretation here and this one here. Maybe the mathematical parallelism is suggestive, but what we're rethinking is the philosophical position in both cases.
Yeah, I mean, maybe for me, mathematical considerations come into it but on a more like aesthetic level. Like it's a lot cleaner to do away with a bunch of extra states and things like that you don't really need to make the theory work effectively. Now, yeah, there's things you could say, like, that's just a very, very sort of clean kind of presentation of the theory, which I try to do in the paper. But of course, you might, based on the actual Hamiltonians of systems or something like that, that might add to the interpretive complexity of the theory. There's certain Hamiltonians that we use that are sort of naturally interpreted as being related to particle states and so on. And so then you might say, it really makes sense to have option 1. But yeah, I would claim that you could still reinterpret all of these in the other ways too, but maybe it's more difficult when you're looking at particular systems. But from a general point of view, it's very clean to present things in the third way. So maybe some kind of more aesthetic preferences come into this, but maybe that's right when it comes to interpretation. As long as the physics is all the same, then there's no conflict.
Back to yesterday's discussion, right? Whether this is really an interesting question, we should care more about, standard methodology and explanation, right? In that sense, it seems quite simple to me to say it's incoherent to be Boltzmannian and Everett person, because somehow, if I once have embraced this idea of
Boltzmannian approach.
They hate the Gibson, but they love the Boltzmannian approach, right?
Yeah.
And so they have to, if they're Bohmian, they also have to love Boltzmann, and because their scientific mythology is kind of also corrupted by kind of metaphysics, I mean, strong metaphysics, a priori leaning, so to speak, right? So, I mean, I don't know, but I think in a way it makes sense that people like Brian Roberts claims one thing implies the other.
Yeah, well, if you think of taking a kind of quantum to classical limit that leads to statistical mechanics, like if you consider quantum mechanical systems in general, not all of them are going to have limits that lead to particle state. I mean, it seems like if you're an Everettian and you don't naturally have particles in your ontology, you take some limit of a system, and then you've got to introduce particles at the classical level. Why did you do that? Yeah, it seems kind of like, yeah, unless you insist, well, all classical systems must be particle systems, but why insist on that? The most general limit would just lead you to something that has classical statistical states, probability measures.
And I think it's true that somehow, isn't it the tacitly kind of these Gibson people, I mean, as you can also say, and also they always kind of say, basically, that after all, it's not empirical, but after all, what they say is somehow more correct, it's more general, or it's not. Like, I mean, that's what I got from the Gibsons. And also from people like Wallace, somehow, I mean, after all, at least, for instance, this Bohmian stuff doesn't generalize, right? That's amazing, and same as same things I think to Boltzmann, it doesn't really generalize, it will never work, the same way how Gibson and some of this work, but anyway, so.
Yeah, maybe so, I'm not sure about that. Okay, so should I move on? Next part. Now on to inflation, I think. Okay, so I had you look at this paper by Bell when he talks about quantum mechanics and cosmology. It's a famous paper. Probably most of you have read it before, but if you haven't, I hope it was good for culture. So he in the paper he draws significance to cosmology in relation to the foundations of quantum mechanics, and it's in a way meant to criticize the quote-unquote Copenhagen-esque conception of the theory that takes the idea of measurement as fundamental. So as he says in a joking way, what exactly qualifies some subsystems to play the role of measurer? Was the world wave function waiting to jump for thousands of millions of years until a single-celled living creature appeared, or did it have to wait a little longer for some qualified measurer with a PhD? Yeah. So, I mean, the idea is that if measurement always involves some, human observer, how did anything happen in the universe before there were humans? And so he considers two interpretations of quantum mechanics that he thinks are applicable to cosmology, Bohmian mechanics and Everettian quantum mechanics, unlike Copenhagen interpretation, which doesn't seem straightforwardly, maybe even indirectly relevant to cosmology. So in the paper, Bell's considering the situation of quantum cosmology in the stricter sense that I talked about yesterday, quantum theory of cosmology based on a single quantum state or a world wave function, something like that. In this lecture, I wanted to talk about quantum cosmology more broadly because that's a place where we have a specific example of a quantum to classical transition that's important for understanding cosmology. Okay, so the case that has been attended to most, as far as I'm aware anyway, is the inflationary scenario. This involves explaining a temporal quantum to classical transition in the early universe. Okay, so now I'll talk first about inflationary cosmology a little bit and its fine-tuning problems, which I've written about quite a bit, before going back then to this quantum to classical transition in the early universe. So cosmic inflation is a certain cosmological scenario that was particularly popularized by Guth from his 1981 paper. There are other people involved in the development of the theory around the time too. An important predecessor of Guth that Guth was unaware of was Starobinsky, and some other Russians were interested in a scenario like this. But Guth's paper is really the one that caught a lot of attention and popularized this cosmological scenario. So it's the theory, or if you want to say more broadly, something like a paradigm. The inflationary theory is a fairly malleable theory, which makes us want to call it a paradigm. In any case, the basic idea of cosmic inflation is that the very early universe underwent a brief period of accelerated and in general, fairly general cases, exponential spatial expansion. But the key idea is that the expansion is accelerated. And in this way, it's exactly like cosmological constant and dark energy in causing this accelerated expansion. But the difference is it happens in the early universe and ends. And it happens during a different kind of matter composition of the universe. But there are some analogies anyway. Okay, so this expansion greatly increases the size of particle horizons. If you don't know what particle horizons are, I'll show you a picture that makes it clear enough what they are. In any case, this expansion increases the particle horizon so much that the entire observable universe, the present observable universe, fits within a single causally connected region, which is not the case before inflation, as we'll see in a moment. Okay? So I already said this about cosmological constant or dark energy. So let's go with the original motivations for cosmic inflation. So Guth's motivation wasn't to come up with a theory of structure formation in the universe. His motivations were to solve various fine-tuning problems of the Big Bang model that we talked about yesterday. So I write alleged in parentheses here because it's debatable whether some of these problems are genuine problems for the Big Bang model. I think most of them are genuine fine-tuning problems, but it depends how we interpret them to some extent. And Guth claims that inflation solves all these problems, but it's maybe not so clear that inflation, certainly in its original form, solved the measurement these fine-tuning problems. But depending on how we interpret them, we can say that it solves some of them for sure, I think. At least this is what I've argued in my papers. Okay. All right, so the two key fine-tuning problems have to do with flatness and uniformity. So what inflation does by rapidly expanding the universe spatially, the spatial geometry of the universe gets flattened through this kind of dynamics introduced by inflation. And also, by spreading everything out, in effect, it makes the contents of the universe more uniform. Okay? People might make analogies with the surface of a balloon. You can imagine, like, if a balloon's very curved and you expand it, the curvature flattens, and if there's some inhomogeneities on it, if the balloon stretches, those inhomogeneities flatten or become more uniform. So that's just a rough picture, I guess, that maybe is helpful for understanding how inflation, an expansion like inflation causes, could have these effects. Okay, so I mean, the two problems that are most discussed in the context of inflation are the flatness problem and the uniformity problem. Actually, usually people say the horizon problem here, but it's not exactly the horizons that cause the fine-tuning problem. It's sort of an obstacle on the way to solving a more pressing problem, the problem that really matters, which is the apparent uniformity, homogeneity, and isotropy of the universe. Okay, Guth was also concerned with another problem that arises only with symmetry breaking in grand unified theories, which in the 70s and 80s, where it was understood this would lead to the proliferation of magnetic monopoles. So this was called the monopole problem. Okay, so let's talk a little bit about the flatness problem. So the basic fact that we can infer from observations, the one that suggests the flatness problem, is the universe has a nearly flat spatial geometry, or Euclidean, you could say. So given the general FRW models, it seems like the spatial curvature of the universe could be curved, positive, negative, or flat. It seems like there's a lot more possibilities for it to be curved, so why is it so close to flat? Okay, but maybe more specifically, flatness is also dynamically unstable. Remember, I talked yesterday about the Einstein static model being unstable, and this was enough for Einstein to give up on it. So flatness in the FRW dynamics also has this instability. So actually, if something's a little bit curved in the early universe, it should become more curved over time. So it seems like there's relatively few initial conditions that could give rise to the kind of flatness that we see today. So that is to say, a narrow range of initial densities of matter could have resulted in the universe we observe. And if we try to give a probabilistic interpretation to this, it seems like flatness is quite unlikely. Okay. So what inflation does, though, by putting in a field or whatever that leads to exponential expansion in the early universe, we reverse that dynamical instability. We make, as it were, flatness an attractor solution in FRW dynamics. And so, depending on a wider range, at least, of initial conditions, the inflationary dynamics forces the spatial curvature of the universe towards flatness. Okay, not just any initial conditions, but a wider set of conditions, right? It's sort of like a narrow range of initial conditions in the normal FRW dynamics would only be allowed in order to get flatness as close as we have it now, whereas with the inflationary dynamics, a much wider range of initial conditions could lead to flatness at the present time. Okay? So if we think of the flatness problem as just a matter of the instability of the FRW dynamics with respect to flatness, then we can say inflation solves that. Sort of obviously, it just reverses the stability. But if we think of it as a fine-tuning problem that requires a probabilistic interpretation, I mean, it's not so clear. Like, okay, there's a narrow range of initial conditions that could lead to flatness today in the normal Big Bang dynamics. Now it's wider, but it's still, like, relatively to all the possible initial conditions, a pretty narrow range. And so it's not clear, given a probabilistic interpretation to the range of initial conditions that could lead to flatness, whether inflation solves that as a fine-tuning problem. It's still fine-tuned, in other words, but not as fine-tuned. Is that a solution? Maybe a bit, yeah.
Could we widen that range by having more inflation? Sort of longer periods? Or
sure.
Even stronger growth, more inflationary, hyperinflationary growth?
Yeah. But it's still, like, given the total range of possible initial conditions. So, I mean, initially, I'm not sure Guth thought this, but it seems like he and maybe some others did, is that no matter what initial conditions you have, it'll move towards flatness. And that's not quite true for, various reasons.
Is it not quite true, or is it not true at all?
Well, I guess you could say it's just not true at all.
Okay. So it improves a little bit, or on the problem?
Well, I think that's the thing. I mean, if we try to measure this quantitatively, it's a bit hard to measure this quantitatively. And this, because it's hard to, basically the problem is it's hard to put a measure over these initial conditions. Yeah, and so it actually really just doesn't make sense in the cosmological context to give a probabilistic interpretation to these fine-tuning problems. Yeah, I mean, so something feels wrong, but how to interpret what's wrong about fine-tuning is a complicated matter, I think. I mean, that's what a lot of my research has been on, in trying to understand what the problem with fine-tuning is in this context. Okay, so let's go on. The second problem, the horizon problem, as it's generally called. So the problem that's, the basic empirical fact, rather, that suggests the horizon problem is the existence of the cosmic microwave background radiation, the CMB, having a high degree of isotropy. And if we assume we're not in a special place, like I talked about yesterday, the Copernican principle, then we think that not only is the universe isotropic, but it's homogeneous. So I'll just use the word uniformity for this, homogeneity and isotropy. Okay, so it seems like the cosmic the CMB suggests that the universe is shockingly uniform. And we can ask, how did this uniform state come about? So the Big Bang, the default Big Bang explanation is that's just the way it started. What's wrong with supplying some initial conditions like this? There's no explanatory problem. If it started with those conditions, then this is what we'll see in the CMB. But cosmologists feel a little uneasy with these initial conditions. They think they seem too special, and they would prefer, one might say, I guess, a more dynamical explanation for uniformity. It seems like a special condition. That special condition, it seems like, could only come about if it was forced to come about through some dynamical mechanism. Like we shouldn't just posit initial conditions like this. Is the kind of feeling, okay? But any dynamical explanation of this uniformity is precluded in the Big Bang model by the existence of particle horizons, which I've already alluded to. And it's this obstacle here for dynamical explanation, part of the particle horizons, that gives rise to the name, the horizon problem. Okay. So I borrow these pictures from Erman and Nosterin's paper, A Critical Look at Inflationary Cosmology. So you can just see the particle horizon here. Maybe I'll stand up now and try to point out what's going on here. So this is the Big Bang model here. The Big Bang sort of starts at t equals 0. This is the time of decoupling when the CMB was created, as it were. And so imagine a point, and we're here at time t0. Okay, so this is our backward light cone here, looking back, and we can look in opposite directions of the sky and see the CMB here at point y and point x. In the opposite direction, they have essentially the same temperature. How could those 2 points in the sky have almost exactly the same temperature as the wonder? Well, nothing dynamical could have caused it, because this is the backward light cone of this point y here, going back to the Big Bang, and this is the one going back here. So all the causally relevant influences on x and y come in the backward light cone, and they're not overlapping at all. So there's nothing that happened in the history of y that could have affected x and vice versa. Yeah, so those are the particle horizons. That's the horizon problem in a nutshell there. So then what inflation does, inflation sort of, this is the start of inflation, this is the end of inflation. Inflation happens during this period. Maybe it's a bit hard to see in a static diagram like this, but in short, introducing this phase of inflation causes the backward light cones x and y to overlap, so that there's at least a possible dynamical explanation for why they have the same temperature. Does that make sense? Well enough? So, if we wanted to describe the horizon problem as just a problem of getting overlapping light cones, then sure, inflation solves the horizon problem. But that doesn't solve the whole problem yet, because just having overlapping horizons doesn't necessarily do anything without explaining what kind of dynamical mechanism leads to uniformity. Okay? So that's what I've said here, right? Horizons prevent dynamical explanation of uniformity of cosmic microwave background radiation. Accelerated expansion makes it so that the causal paths of these different points in the CMB do overlap, but overlapping causal paths don't guarantee that the CMB will become uniform, or if we try to think of the dynamical explanation being one of equilibration, thermal equilibration, then yeah, that's impossible without overlapping light cones, but just, having overlapping light cones doesn't mean an equilibration process will happen either. Okay? But inflationary theorists think that inflation doesn't just solve the horizon problem, they think it solves the uniformity problem. But it kind of does by default as well, because of what I said earlier, like if you take some inhomogeneities and rapidly expand them, they're going to get stretched out and everything's going to become more uniform. But that's kind of a bad solution in this context, because inflation stretches everything out so the universe becomes practically empty. But the universe is not empty, right? So inflationary theory, in order to solve this new problem, as it were, is to introduce a post-inflation stage, which is called reheating. And here the universe is repopulated with matter in a way that makes the post-reheating phase like the initial conditions that we need in the Big Bang, right? A hot, dense state. Okay? And the sort of mechanism of this is to imagine that there's a field driving inflation called the inflaton, and the inflaton decays into standard model particles from a kind of particle physics point of view. That's what's imagined to happen. Now, I don't know a lot about reheating. I've never studied it in detail. It's very complicated. But if inflation is going to be viable, there has to be some kind of reheating phase to give the appropriate initial conditions for the Big Bang universe that continues after inflation. Okay. So that's just a bit about the fine-tuning problems. Are there any? So I'll stop there because now I'll go on to talking about structure formation. Do you have a question?
Yeah. So it's not about the heating. So not easy questions, but so this beat just comes after the inflation that one says this is kind of microprocess. I don't know, or some kind of low level, like nuclear. Not nuclear, but that's not.
Yeah, kind of. I mean, it's like a decay process.
Yeah. Okay. And this is a really complicated, nuclear / particle physics, which you have to look at in detail. You can't put it on a diagram anymore, right? Something like this, right? That's how we should think of it. Yeah. And it's supposed to be generic, right? Just really.
Well, it depends on the kind of particle physics you introduce.
Yeah.
Again, I never really studied reheating. I think it's fairly complicated. You need it to make the whole story work. There's various proposals people have been working on since the 80s on how this works, but I don't know the details.
But it's something I could look into, right? I could wonder, like, this is a place where we can also take this claim to have Sigmund and fine-tuning, right? So maybe it comes in there as well, right? So,
yeah, maybe. Once we move to a kind of field theory story, I think there's a lot of possibilities you can cook up in QFT for coupling fields in various ways. So I think there's a lot of room for trying to make a reheating phase work. But it's all like new physics because the inflaton is not part of the standard model of particle physics. So usually people use a scalar field for the inflaton because it's quite a simple field to work with. But then you have to think about how it couples with standard model particle physics.
And so if you never understood either, so this is something which is sometimes supposed to be linked to the Higgs particle even?
Well, originally that was the idea.
Yeah.
And as Urban and Mosterine here point out, they think that that was a great idea. If we could link the physics in cosmology to known standard model particle physics, and it all works, that would be amazing. Well, sure, it would be amazing, but it definitely doesn't work. I think some people still play around with kind of Higgs ideas in inflation, but most people think that can't be right. We have to introduce new physics, and rather than, in a way, this opens up a lot of speculative possibilities then to just say, well, the inflaton is a new field, so let's see what we can do. So then moving in this direction already moves you to beyond standard model particle physics.
This is good because this is all perfectly, right?
Yeah.
So the inflaton could also be modeled as some more sophisticated field rather than a scalar field. So
it's less popular to try these, but definitely people have tried multi-field inflations and complicated scenarios for sure.
Yeah, I see. Yeah. Okay, that's good.
Yes.
Sorry, can you go back like 2 slides?
This one?
The one where you have like the attractor.
This one.
Oh, that one, yeah. Can you see like how flatness, like why is it then an attractor solution?
Well, without drawing, I guess, more complicated diagrams, I think just the balloon analogy is meant to capture that, right? If you expand a balloon rapidly, its exterior curvature just gets flat. Yeah, no matter what, it gets flatter. That's the idea. Whereas if you shrink a balloon, it gets more curved. So the Big Bang dynamics is more like the shrinking balloon, but accelerated expansion reverses that. That's roughly the idea. If you want a more precise one, I have a paper of it. Well, I mean, lots of people have explanations like this. This is the normal way people talk about the flatness problem, I think, is about this dynamical, in this dynamical way. But also people talk about it in terms of likelihoods and things like that, but I think that's a less good way of understanding because it's not really clear that inflation solves that fine-tuning problem if we interpret it probabilistically. But if we interpret it as a dynamical stability problem, then we can definitely say that inflation reverses that, or solves that. Yeah. Okay, right, so So initially, these inflationary solutions to Big Bang fine-tuning problems were seen as the main motivation to pursue the theory. But a more empirical motivation soon took center stage after Guth's initial proposal. And it was very soon after. I forget when the first papers appeared about structure formation and how inflation could serve as the sort of mechanism for seeding the initial perturbations required for structure formation. Yeah, maybe in Guth's paper was in 1981, and they were already having workshops about this in 1983 and 4. So it was pretty quick after. So the period where the fine-tuning problems were the main motivation, I think, was relatively short. Nevertheless, these fine-tuning problems are always introduced whenever inflation is introduced in modern textbooks and reviews, always, yeah. So it's still kind of seen as theoretically important somehow. But from an empirical point of view, it's what the possibility of providing a theory of structure formation that really makes inflation a part of the standard model of cosmology, the lambda CDM model. I mean, insofar as people think of it as part of the lambda CDM model, which, yeah, some may think is controversial. Okay, right, so the basic idea, and still the kind of main idea, is to consider linear perturbations to the metric, the gravitational metric, and the scalar field also driving inflation. Okay, and that again the term that's generically used for the field driving inflation is the inflaton. So then we treat these perturbations, these linear perturbations, as quantum fields on a classical homogeneous FRW background. And so in other words, we use a semi-classical treatment of gravity. And so in this sense, it falls within quantum cosmology in the broad sense, using a kind of quantum gravity at low energy in Wallace's terms. Okay, so then the quantum fluctuations in these quantum fields are understood to freeze whenever a mode of the field, a mode with a particular wavelength, gets stretched and leaves the Hubble radius during inflation, because inflation is stretching the modes out through the accelerated expansion of the background metric. Okay, so then this freezing is generally understood to make the modes classical. Okay, so quantum correlations in the fields, in the quantum treatment, when they leave the Hubble radius, are understood to transform into classical ensemble averages. So we go from quantum to classical. Okay, and these classical ensemble averages are the things then that we would use to compare with the anisotropies in the cosmic microwave background radiation, which we measure. Right? When we look at the small inhomogeneities, or anisotropies more specifically, in the CMB, we can do a statistical analysis of those. That statistical analysis is what we want to compare to the predictions of this semi-classical prediction. Okay, so these modes get stretched by inflation, and then we see them when they come back within the Hubble radius in normal Big Bang expansion. These modes come back in within our horizon. Okay, so roughly then, the cosmic history of structural formation looks like this. This is a popular picture, I think, from Planck. The idea is, this is the Big Bang universe. Big Bang starts here with singularity. Then we have a phase of cosmic inflation that gives the origin to the quantum fluctuations of the inflaton, seed the seed perturbations that lead to structure formation. Okay, so then we get to various different phases when particles first start forming. This is after reheating. Ordinary particles, a couple of the light and dark matter particles, and these inhomogeneities then under gravitational attraction and other processes start forming small scale structures at first. During this phase, the recombination is when the cosmic microwave background gets formed, because after this point, the photons that make up the CMB are no longer interacting with other things. They get frozen out. Okay, and then there's a long period where dark matter plays an important role in forming large-scale structures. And eventually these form into stars and galaxies and so on. This is kind of an accelerated story of the history of the universe, but the point is just that this is a critical thing. Like if we want to understand how things like galaxies form, the things that we can see when we do galaxy surveys, and how the CMB forms when we look at the CMB with the Planck satellite and so on, we wonder where these small anisotropies come from, and inflation is back here. It's supposed to give us the story, the kind of the theory of the initial conditions of structure formation. Okay, so what's distinctive about inflation is that when we use this semi-classical treatment based on coupling of a scalar field to gravity of the inflaton, it yields these characteristic predictions for inhomogeneities in the CMB, very particular ones. And these predictions of inflation were subsequently confirmed when satellite observations with sufficient resolution were made. So WMAP was, I think, in the 90s, and Planck in the 2000s and 2010s were doing their observations. So at the time that inflation was developed in the 80s to make these kind of semi-classical predictions, there were only like the barest hints of inhomogeneities in the CMB spectrum. The COBE satellite didn't have sufficient resolution to really pick out any inhomogeneities. Maybe there was like barest hint or so, but theoretically people thought that there were inhomogeneities in the CMB to be found too. It wasn't perfectly uniform, but it's not like the predictions that were made by inflationary theorists were motivated empirically in any way. Like they came up with the predictions of the theory, and then later were able to check them, and they were spot on. Okay, and when I say characteristic predictions, the point of that is to stress that they're not very generic predictions. I mean, to some extent, some aspects of it maybe are generic, but so far, I think it's fair to say that no competitor theory has matched the inflationary theory in its predictions, at least without introducing considerable complications in fine-tuning. And so, I have never done a careful analysis of this, but I think you could say that one has to think that inflation is at least moderately, maybe even strongly confirmed by these predictions. Maybe if we find more alternative theories that can match it, that would decrease our confidence that inflation has something special about it that makes these characteristic predictions.
Can you say a little bit more about how generic or in what sense inflation predicts these?
Yeah, well, I mean, that's the most I can say, really, is that no competitor has matched this. Inflation gets it pretty much spot on. But I do think
inflation gets it spot on.
Well, I'll show you the picture that normally gets shown here in a couple of slides that indicates some of the features of it. But I think, I don't think anyone has done a careful philosophical analysis of this from a more confirmation theory point of view or so. So I think that would be worthwhile to get a better sense. But this at least is what I think, is the kind of default opinion, is that we have to kind of go with inflation because it gives us a theory of structure formation that's predictive, and we don't really have good alternatives. I mean, some alternatives, bounce models and things like this get some of the predictions, but it's a little harder with those models to get them, whereas inflation just spits out the right story, in the simplest kind of way. Yeah.
So you're not very convinced by Robert Runberger's paper, for instance, where he...
Well, I think he admits, this...
Oh, he does admit that?
Well, I think so, yeah. It's been a while since I read it. I meant to read it again before this one, but... I think if I remember right, he says, well, it's just not true that no other theory can predict this.
Okay.
But, I mean, of course you can contrive some theory. It's not easy, I think, and those theories aren't really fully worked out, I think, at least not as much as inflation. Inflation says, here's a field, we do a semi-classical story, we know how to do that very well. It gives these predictions, it gives a certain spectrum of anisotropies, and that's what we see. Yeah, they don't match, the cleanness of that story, I think. But I think what he thinks is that we shouldn't just assume inflation is the right story and forget about alternatives. We need to look and see. And so I think that's why I said there's still scope. We can't really assess, and this fits with the meta-empirical assessment story that I want to give in the next lecture too, is that, and this is a sort of general Bayesian thing, without assessing the alternatives, we really don't have a good grasp on how well confirmed anything is. So yeah, inflation is confirmed in some sense. How much, we can't say quantitatively until we have a sense what the alternative possibilities are. So far, it doesn't seem like the alternatives are quite as good, but yeah.
It's a weird question, but like, how important is this prediction? In the sense of like, the CMB is like quite homogeneous, so like I guess the inhomogeneities are like super small.
Yeah, like 10 to the 5th or 6th or something like that. One part in, yeah.
Yeah. So, I mean, like, is it like a puzzle? Like, it's, I don't know, like, it's something like that we need to solve in the...
But if we want a dynamical story for, how we get exactly these small inhomogeneities in an otherwise homogeneous universe, yeah, then you need some kind of story. I mean, you could just say, Big Bang model posits these exact inhomogeneities that are required to give rise to structure formation, but like there has to be like very precise correlations at the Planck scale or something like this if you just throw it in the initial conditions. And for the reasons like you were saying yesterday, this seems like a wildly implausible story. Yeah, so then inflation says, okay, well, let's move away from the Planck scale a little bit. Posit a scalar field that drives inflation. It's a quantum field. It has fluctuations that get frozen out, and then voila, you get the story. I mean, you could posit initial conditions. You could say, well, forget about all this high energy stuff. We'll just posit the initial conditions at some nice friendly time, and then you just have an explanation from initial conditions. And I mean, and really, like the physics involved isn't super complicated that leads to these inhomogeneities. And so, yeah, you might not have complete confidence in all aspects of the inflationary story, but you need something that works kind of like inflation to see these inhomogeneities as kind of the upshot. Yeah, it may not be inflation exactly, but it has to have a lot of very similar characteristics in inflation to give this exact spectrum.
So you would say like it's as puzzling as the flatness problem, for example?
As the what, sorry?
As a flatness problem, or like the...
Well,
I mean, so
I never thought about comparing.
So there's a difference between like the prediction of inflation and like the motivation for proving inflation.
I think scientifically it's more desirable to have a story of structure formation. The flatness problem, I mean, as Ehrman and Mosterin put it, they think, wow, this is just a problem of explanation, and different people have different standards for what's a good explanation. And so you might think of the flatness problem as more of a philosophical problem, like I was talking about earlier. You may not be bothered, but I mean, it doesn't seem to be a merely philosophical problem, because trying to come up with a solution to the flatness problem leads to a theory that can also explain structure formation. So there's something going on there. So if you think about like David's meta-empirical confirmation, one of his schemes is the unexpected explanatory coherence. Well, inflation might be seen to benefit a bit from that. By just positing a brief period of exponential expansion in the early universe, we can understand flatness, uniformity maybe, seeds for structure formation. It seems to yield a lot with a very kind of simple idea. That seems attractive on the face of it. How good of an idea it is, it's really hard to know until we've really explored the space of theoretical alternatives. Yeah, but so far, maybe it's too much to say it's the only game in town, but it's the lead horse, I guess you could say.
By characteristic predictions, do you mean the near Gaussian?
Yeah, things like that.
Okay.
Yeah, I have it on one of the slides. Yeah, so this is the story of the different satellites that made observations of the CMB. So, like, if we kind of color this a little bit to get a sense of its resolution, what kind of inhomogeneities it saw, like Kobe just saw basically a single color. Okay, but that's enough to say that, wow, the CMB is extremely uniform in the large scale. WMAP had a much higher resolution. There you can get good statistics about the inhomogeneities. Planck had an even higher resolution. It didn't really change the story, the general story, very much from WMAP, but it was a good check because there could still be some errors with the W map results. So Planck was like a very careful check to make sure that the W map results were good, and did some other things too. So anyway, yeah, this is the state of the art really. The Planck satellite has the best data you could hope for. You really can't do, even if you had a higher resolution, you couldn't get probably better data than Planck. So then here's the kind of famous chart from Planck. I'm pretty sure this is Planck. Yeah. So this is a kind of a sky map of the CMB. So the reddish ones represent parts of the sky that are hotter, and the blue colder. But these fluctuations are actually very tiny. This makes it seem, the color scheme makes it seem like there's a dramatic difference. Yeah, again, this is like, you know, the difference is like 1 part in 10 to the 5th or 6th or something like that. So it's very tiny inhomogeneities that you see in the CMB. But these are understood to be the seeds for that for structure formation. That is, you know, these inhomogeneities are the things that later lead to a kind of, well, there's some additional stuff in between, but eventually we get to the point where we have gravitational attraction causing stars and galaxies and so on. And if you do a similar, I didn't put this up, but you could do a similar sky map from galaxy surveys, and it's also very striking to see how these two maps are exactly the same. Right? So you can understand it's these inhomogeneities exactly that give rise to the distribution of galaxies that we see. Like basically the universe is empty, but there's galaxies, and they cluster right around, you know, like these hot spots and so on. Okay, and then the picture on the left, we can talk about the different wavelengths or angular scale that measures the inhomogeneities. So it's small scales up at the height, or like if we take little patches and look at the homogeneities on that scale. Down here is if we sort of chop this up into big sections. But some interesting stuff happens here. So on this, the vertical axis is a representation of temperature fluctuations, sort of related to the amplitude. I'm not sure if I put any equations to explain this, but this is understood to be a power, statistical power. And so there's a lot more power in fluctuations around the angular scales, like roughly 1 degree and half a degree. And so this has structure in it, right? These fluctuations have a pattern, in other words, that may be a little hard to see just looking here, but when you do the statistical analysis based on chopping this up and looking at different modes of the fluctuations, you see that certain angular scales have much fluctuations are clustered, as it were, around these angular scales, and less so in these troughs and so on. Yeah, and so there must be, I mean, we expect when we see structure like that there must be a story for how that happened, and indeed there is. So one thing I guess to say is that the red dots are the observations, like the statistical analysis here, and that curve represents the prediction, the inflationary prediction of where power should be. And you can see it's like a perfect match. Yeah.
So I have 2 questions. The first one is I've always been a little bit puzzled about how the multipole moment sort of seems to be going exactly with the angular scale, or I mean how?
Yeah, those are the same. It's just 2.
Those are the same.
Yeah, I mean,
so
yeah, it's like, I mean, I don't know. I mean, it's roughly like the difference between wavelength and angular number, or something like this.
Let's see.
Yeah.
Okay. Good. That's very helpful. Thank you. And now, of course, I want to know more about the green line.
The green line.
The green line.
Wow, you need a book to do that.
Okay, but I mean, that's the prediction of inflation. So I want to know, what does that mean to predict that? What assumptions do we make? How generically
There's a lot.
is it? And so on and so forth. I mean, there must be a big and important story how we get the green line.
Yeah, I mean, you know, there's textbooks that go through this entire process of yielding this prediction, like the Dawdelson book, or Little and Lith, or Bauman, I think, does it too. And I mean, it's like 10 chapters of work. So I mean, I've worked through this, but I don't think I could just give you the quick story because it's
not even a quick story, very superficial. So I mean,
yeah, I could.
A sense of how generic of a curve?
Well, that's the important thing. Yeah, I mean, I would say it's not a generic curve, but I mean, if you work through the details, a lot of the details that give you that curve are just normal physics, like standard model kind of physics. But you need something that gives you, yeah, well, so you know, if we go back to this story here, what we started with were linear perturbations to the metric, and I guess that's the basic thing. Yeah. So we need something that. Yeah. So we could try to do this all classically, but this, and there's a paper by Schiffrin and Wald, I think Schiffrin, Wald and someone, that tries to give a more like classical hydrodynamical kind of story that works with giving the initial conditions like this. But it looks like you need to make some pretty wild assumptions, like I was saying earlier, if you try to give a purely classical story. If you try to give a quantum story, you need something that it makes sense to talk, like assume certain things about the quantum field, how it couples to gravity, and so on. So we are assuming like linear perturbations to the metric. So yeah, we are putting some initial conditions into the inflaton field as well. But like, yeah, if you make these sort of simple assumptions that there's an extra quantum field that's a scalar field that is a linear perturbation of a uniform scalar field, and then you work out pretty standard physics after that, then you get that prediction. That's the best I can do, I think, on this.
Okay, thank you, that's already something. It's sometimes said that the assumption of the potential being simple have been shown to be ruled out empirically somehow, or some simple models are hard to connect with that. I assume that's with this, right?
Well, yeah, I mean, yeah, we have to go into something else. Like, so that's talking about the potential for the whole inflaton field.
Yes.
So you get the linear perturbations because inflation has to happen in a slow roll inflation.
Sort of a plateau or...
Yeah, so there has to be some portion of the potential where the inflaton can slow roll down it, and that's the sort of crucial assumption in order to give rise to the linear perturbations. But the potential could be complicated elsewhere in all sorts of different ways.
But it doesn't have to be.
It doesn't have to be, but Planck rules out certain shapes of the potential.
Okay,
like
so
all of them have to have some slow roll portion in order to give rise to this story.
Okay.
Yeah, elsewhere there's plateaus and hats and all these other kind of things. Some of the different potentials are ruled out by observations. They couldn't be quite like that, but
okay, I see. So, but that's what Ias and Tol mean when they say that classic models, I think that's their word.
Well,
ruled out. We need postmodern inflation.
yeah, they.
Or is that?
I forget. Well, I forget exactly what they mean by classical inflation, but it's a certain kind of potential, one that was assumed as the most natural one early on. Yeah, that's been ruled out, but I think they made a little bit of a confusion that was pointed out by some other physicists shortly after, that they were mixing up two different kinds of potentials, like a hat versus a plateau or something like that. And then this sort of distorts what they say a little bit. But Richard and I didn't really pay too much attention to that because it didn't affect our argument. So yeah, I can't remember exactly what the difference is. Okay. Yeah, okay, so this partly answers one of the things you were asking earlier. So if we assume that the power of a particular mode, which here I just give by a wave number k, follows the power mode, then, power law, then the CMD data suggests that the spectrum of the inhomogeneities in the CMB is first approximately scale invariant, which means the power is approximately constant. The amplitude is small, so the amplitude A is much, much less than 1, and approximately Gaussian, as given by the spectral index in S in the exponent, that's approximately 1. And those are some of the key features that come out of the inflationary prediction. Okay, so like I've said a couple times now, if we just naively retrodict this spectrum using classical general relativity, relativistic hydrodynamics, this results in all these modes being generated beyond the horizon in an acausal way at early times, high densities. And so it seems to run afoul of the horizon problem. Like, how could we have these particular modes being generated in an acausal way? But you could, I mean, if you want to, just assume that this happens, and then you don't have to invoke any quantum theory, or, well, not any, but you don't have to invoke anything about inflation if you're willing to assume, extra horizon generation of particular modes of inhomogeneities. Okay, and again, this is, I think, this is something written up by. I mean, this particular sentence more or less comes from this Schiffernan wallpaper. I think it's Schiffernan. Okay, but in any case, yeah, these predictions, though, are, and when I say closely, I mean extremely closely, they match the generic predictions of slow roll inflation. The other thing that we get, these are just scalar inhomogeneities or fluctuations that are produced here, but inflation also generally predicts gravitational waves also being generated. And so far those haven't been detected. But if we detected gravitational waves that were in line with inflationary predictions, then I think inflationary theorists would just say, yes, we've won, because that would be very hard to get both of those things. So far that hasn't been detected, even though there's been some false alarms about this some years ago with the bicep observations, that probably some of you have heard of. In any case, nothing's been seen about primordial gravitational waves. So that's still left out as a prediction that comes from this analysis, inflationary analysis, but hasn't been observed yet. Okay. Finally, now we finally talk a little bit about the quantum to classical transition. So this whole story, like I said before, like if we go back to this slide, right, at some point in this general story that inflationary theory gives, quantum correlations in the field are understood to transform into classical ensemble averages. So how does that happen is quite a natural question to ask. Okay, so if we agree with Bell that quantum theory applied to cosmology has to be a quantum theory without observers, then it seems like we need some kind of interpretation of the measurement problem that doesn't depend on measurement or observers in order to explain how this quantum to classical transition happens. And initially people didn't say much about this problem in the 90s and so on. Kiefer, I think, started saying a little bit, but Kiefer generally writes that decoherence is enough to solve the measurement problem and forgets about it. Then, some people that are interested in quantum foundations started writing about this, started paying attention to the quantum to classical transition, because it seems like a real live case where a quantum transition happens. It has to be with a quantum theory without observers, and so people interested in stochastic collapse theories and Bohmian theories started working on this, especially in the last 15 years, I would say. There's been a lot more papers about this. So Sudarsky's written more than anyone, I think, about stochastic collapse theories, but there was some earlier work by Peter Martin and Venon. Bohmian theories, Valentini said some things, not really specific to cosmology, but related. Bort Straube has now sort of taken up this, along with a Brazilian physicist, Pinto Neto, and his team. They've taken up the Bohmian theory. Since Bell and even before, an attraction to the Everett interpretation has been its applicability to quantum theory. But interestingly, I think, when I first started looking into this, like 10 years ago actually, nobody had really tried to take the inflationary story and its quantum to classical transition and give a complete account for it in the Everett interpretation. And so this is something I did at the first Foundations conference I went to in 2013. I gave a talk about this, but actually never published the paper. But I tried to work out exactly how we should understand this quantum to classical transition from an Everettian point of view, in particular following Wallace's account. But now I see Wallace has gone ahead and done it himself. So that's the other paper I assigned, is what Wallace says. And when I gave this talk in 2013, I would say, like, what seemed to me like what Wallace would have to say is what Wallace ended up saying. So I don't really have anything new to add. I can't say anything like, well, he says what he has. But also, I think, so Carroll also touts the Everett interpretation and its application to cosmology, so I put his name up there as well, but I don't think he has written a paper where he sort of details how the Everett interpretation would apply to this case. So I mean, this is the way I kind of worked it out myself. So in Wallace's paper and his talk here last year, he doesn't go into quite this level of detail, trying to use the classicality condition from his book, his 2012 book, where he identifies, using the kind of decoherent histories language. We talk about histories as a sequence of time-indexed projection value measurements, PVMs, and we talk about a history space when we look at all the possible histories generated from the sequence of PVMs. We need decoherence to solve the measurement problem in the Everett interpretation, according to Wallace, right? And so we can conceive of decoherence happening by looking at it as a function on pairs of histories in this space. And then we can say that the history space is decoherent if the decoherence functional between any two incompatible histories is 0. And then the important thing for the Everett interpretation is to show how decoherence leads to branching, so that we have the many worlds. So if the history space satisfies the decoherence condition, it has a branching structure. So this is just Wallace's story about how we get decohered worlds. So can we apply this to the quantum to classical transition in inflationary cosmology? So, like, as you know, decoherence is essentially the suppression of interference with respect to a system's macroscopic degrees of freedom by interactions with microscopic degrees of freedom. And this can be some kind of environment, either internal or external. We can split the system in some way between system and environment. Okay, so, arguably, decoherence doesn't solve the measurement problem per se, but we can ask whether it places a constraint on quantum theories of structural formation, and this was a question I was kind of interested in, but it seems like the answer, I take it, at least in this scenario, is not really, because when you look at the literature on the quantum to classical transition, just the physics literature, stuff by Kiefer and others, and also Kiefer discussed this in his talk last year here, I saw. So decoherence has been shown to occur in many, many ways in this scenario. There's lots of possibilities for decoherence via external scalar fields, internally with short wavelength modes, nonlinear coupling between different modes within the same field, spatial entanglement, thermal fluctuations after reheating. Like, people have come up with decoherent scenarios in so many different ways that it seems like, decoherence just happens. One way or another, it has to, and so there's no real problem here, I think, for the Everett interpretation. If we say that the Everett interpretation has to work through some kind of decoherence, but decoherence happens very easily, then it doesn't look like requiring decoherence to solve the measurement problem puts a real constraint, at least in this scenario. Yeah, so it's maybe kind of like a negative result here. You might think, that could be, if decoherence has to happen in a particular way in this scenario, then that would be an interesting constraint, that we have to expect to find this, but it looks like decoherence is easy to come by in this scenario, so it seems like the Everett interpretation should have no problem meeting these requirements, basically. Okay, some closing remarks then. Ease of generating decoherence in the inflationist scenario. It's further evidence that decoherence is ubiquitous in the early universe. There's lots of coupling and entanglements happening. So we should conclude that the Everett interpretation only places a very minimal constraint on theories of structural formation. I guess the way I'm thinking about this, I didn't explain, would be that, one way to make the measurement problem, maybe empirically relevant is to try to find some constraints in actual scenarios, and cosmology might seem to offer this, but in this one at least, it doesn't look like it. It's you might say then that actually, like people said in, I don't know, the 60s and 70s afterwards, the evident interpretation really is very good for cosmology. It fits it quite well. Okay? I mean, maybe there's still some lingering questions we could have. So what counts for the ubiquity of decoherence? It seems to have to come in the dynamics in some way. And therefore, like, the ubiquity of decoherence does give a direction of branching. What kind of initial conditions are required for this? These are some additional questions we can ask. Contrasting though, so insofar as we agree with Wallace and others that decoherence is required in the evident interpretation, when we look at the other approaches to explaining quantum classical transitions in quantum cosmology specifically, they don't literally require decoherence to obtain a solution. Why? Because Bohmian requirement approach enforces classicality by fiat, by including classical variables in the guise of hidden variables, particles, or whatever. Bohmians often will say, though, that decoherence does contribute to certain classical expectations, so it's a bonus if decoherence happens, but it's not necessary to explain classicality, whereas it is for the evident interpretation. Also, the dynamical collapse approaches, they enforce classicality by its dynamics, by the dynamical collapses. But, also most dynamical collapse theorists, I think, would say that decoherence can be understood to contribute to the process. Although I heard Sudarsky say last summer that decoherence doesn't happen in the universe, so I found that very confusing at the time. But anyway, so it's at least possible, I guess, given their solution to the measurement problem, to question whether there can be decoherence at all in the universe. Why? Because, Sudarsky's reason is that there isn't any natural physical split between system and environment, but I don't know, I feel like that's not the point of decoherence in this context. You can make this split to see whether decoherence happens. If it happens, then that contributes to some sort of classical expectations, or in the evident interpretation, contributes to, the classicality that comes through the solution to the measurement problem that the evident interpretation gives. Anyway, that's the end of the talk. So these are some of my papers I put up here that I used, that this lecture is built on, if you want some specific references. And that was it. So thank you very much.